If the crankshaft stops turning, the engine is finished. No crankshaft movement means no compression, no power, no vehicle movement, and no work getting done. Every single force inside a diesel engine eventually passes through one crucial component, the crankshaft. In this video, you'll learn what the crankshaft actually does, how its design handles massive forces, and why crankshafts fail in the real world, and how you can diagnose engine problems. At its most basic level, the crankshaft does one job: convert linear motion into rotational motion. Pistons move up and down, and the drivetrain needs rotational movement. This crankshaft is what connects the two. Here's a simple analogy. Think about riding a bicycle. Your leg pushes the pedal up and down. The crank arm turns that motion into rotation. Inside the engine, the crankshaft does the same thing, except it handles explosions, not leg power. So let's follow that path of force. Combustion pushes the piston downward, and the piston pushes on the connecting rod which it is attached to. The connecting rod pushes on the crankshaft rotates. This power then flows from the rotating crankshaft to the flywheel, through the transmission, down the driveline, and ends up at the wheels. Now, if one cylinder isn't firing correctly, the power output becomes uneven, and vibration increases, which means the bearings can have to take an extra load. Now let's break down the crankshaft into its key components. Number 1, the main journals. They sit inside the engine block and ride on the main bearings. Their job is to support the entire crankshaft. They must stay perfectly round, and they must maintain an oil film to keep them lubricated, as they have to handle constant load. Heavy-duty engines often use large diameter main journals and may have more main bearings for strength and stability. Number 2, the rod journals, or crank pins. Rod journals connect the crankshaft to the connecting rods, and they're offset from the crankshaft center line, and they receive the direct combustion force. Every firing event slams force into the rod journal, and this force tries to twist the crankshaft. This is why oil quality and bearing clearances are so critical. Number 3, crank throws. The crank throw is where the crankshaft function and design truly come together. A crank throw consists of the rod journal, the offset distance from the crankshaft center line, and the arms connecting the rod journal to the main journals. If you measured from the center of a main journal to the center of a rod journal, you'll get a distance that is half the engine stroke. Therefore, the stroke is 2 times the crank throw offset. But why are crank throws offset? Well, that's because if the rod journal were centered, the piston would move, but the crankshaft wouldn't rotate. This offset is what actually creates the leverage. Think of it like a breaker bar, where a short bar gives you less leverage and a long bar gives you more leverage. A larger crank throw gives the piston more leverage to twist the crankshaft. Now, this crank throw length, however, directly affects low RPM torque, engine pulling power, and throttle response under load. All good things for applications needing good power. But here's a critical concept. The longer crank throws mean the piston speeds have to be higher at the same RPM. This higher piston speed means more stress on the rods and pistons, increased heat, and a lower maximum safe RPM. Engine designers therefore have to balance the crank throw length versus durability and operating RPM range. This is why heavy-duty engines favor torque over speed. But these crank throws must be balanced carefully. Each throw carries a rotating mass, which consists of the crankshaft, the counterweights, and the flywheel, but it also carries something called a reciprocating mass, which includes the pistons and connecting rods, as each throw also creates vibration, which is why the crankshaft has counterweights to oppose this. But all engines are not made the same, as different engine designs use different layouts. Inline cylinder engines and V engines are common, and there's also some engines with opposed cylinders as well. But this is why firing order, which is the order in which each cylinder has combustion, and crankshaft design go hand in hand. But back to crank throws for a second. They experience huge combustion shock loads, torsional twisting, and bending stress. Common failure points could include the fillet radii, which is the transition area from the main journals to the vertical portion of the crankshaft, along with the rod journal transitions. That's why these fillet areas are rolled or hardened. And that's also why the surface finish matters so much on crankshafts. But does all this theory actually help when diagnosing things like rod knock, repeated bearing failures, or crankshaft cracks? Well, of course it does. A technician should always consider things that contribute to crank throw stress, such as engine load history, lubrication quality. Crank throws fail because of conditions, not luck. Let's rewind a little bit and discuss the counterweights. Their job is to balance the rotating and reciprocating mass we discussed earlier, which helps to reduce vibration and protect the bearings. Adding weights to these crankshafts obviously makes them quite heavy, but it also allows them to run smoother and last longer under load. This is why heavy-duty diesel cranks are massive. Most heavy-duty crankshafts are made of forged steel. Forging improves the fatigue strength, which allows the engines to handle the high combustion forces. Additional treatments can include induction hardening, nitriding, and fillet rolling, a little more advanced processes than we'll discuss today in this video. But they are all designed to extend crankshaft life. Let's talk about an unbalanced crankshaft. What problems can you see happening if all of that rotating mass isn't balanced? Issues could include vibration, bearing wear, and cracks. Harmonic dampers and flywheels also play a factor in this balancing act as they absorb some of that torsional vibration and help protect the crankshaft from even small imbalances, which can destroy engines at highway RPM. Repairing or replacing a crankshaft ends up being a huge labor-intense and expensive repair. And most crankshaft failures come from oil starvation due to low oil or oil pressure, bearing failure due to poor oil maintenance, or lack of preventative maintenance such as replacing bearings, overloading, excessive vibration, or improper machining. But crankshaft failure is usually the unfortunate result, however, and not the cause. Hopefully you now have a better understanding of how crankshafts work and what they do. But do you know how the camshaft works alongside the crankshaft to actually operate the valves and make combustion work? Well, watch this video next to find out how the two work together.